handy dandy college algebra, PowerPoint. I did have an email, a couple of emails. I had two, and students want me to go over some certain things, so that's why I'm pulling this up first. Slideshow. Wow, whatever. Let's see. Okay, it's not working. Why is it not working? Oh, I have to hit this button. I'm used to dealing with. There we go. Now, did we go over shortcuts? We did that the other day, correct? Okay. Did we write down the exponential laws? Okay, so write them down right quick. So you'll have those as a refresher. Now I do add one extra law, and that's the rational exponent, because in calculus, radicals and calculus do not mix. So whenever you see a radical, the first thing you do is what? Change it to a rational exponent, Hubert. That's right, class. And you'll hear me say radicals and calculus do not mix probably about 5,000 times this semester. So when you get to second calculus and you see a radical, the first thing you do is change it into a rational exponent. Number 4 and 5, those are more for aesthetics. The ones that are really the workers are 1, 2, 3, and 6. You cannot get by with algebra without 1, 2, 3, and well, you can get by without 6. But 1, 2, and 3, you can't get by with. Did we start completing the square? We did that too, right? Okay. All right. I think logarithms are probably next. I gotta hit the button. Okay, that's that. Okay, that's not. This is not the one I wanted. Sorry. Let me go back to pull up. Thought I had it pulled up. Well, let's go ahead and pull up logs. Y'all see logs anywhere? There we go. This is not like. Okay, there's that. Let me pull up the logs first. There we go. Here's the logarithmic properties. You need to write those down. We went over shortcuts. We went over completing the square. You copied down the the exponential laws. Now you need to copy down these. Mostly the product, quotient, power rule, definition of a logarithm. You don't need the z. You can just copy down the top one. So if you wanted to mark this out, that's no big deal. Just copy the top one. And the change base formula. Huh? Yeah. Product, quotient, power rule, and then definition of logarithm and change base. The equality's okay, but that's kind of like the exponent. If the bases are the same, you can set the exponents equal to each other. Do y'all remember that rule? Well, this is the same thing. If the log and the base are the same, if the base is the same on the logarithm, you can set the functions equal to each other. That's kind of a given. But These are just some more things that you will have to know to, manipulate problems in calculus. Change base formula is used because you cannot take the log of a number in your calculator unless it's log base 10, which is LOG, or log base E, which is natural log. So if I give you log base 3 of 27, you got to change it. So that would be LOG of 27 over LOG of 3. And that's how you use the change base formula. I think I show a couple of examples after I do. I give you some examples right here also. Of course, I probably wouldn't leave it log base 3 of 9. I would change it to log of 9 over log of 3 plus log of x over log of, log of 9 over log of 3, log of x over log of 3. But the change base formula is not usually used when you have an x in there. It's usually used when you have numbers. Like log base 3 of 9, those are numbers. Okay. And just to go over, see what else I've got in here. Let me hit this. This one is very important when you solve equations with logarithms. Can you hit that front light for me up there? Thank you. That way people can see it a little bit better. So if we wanted to rewrite these, that would be the log of 12 times 5, which is 12 times 5 is what? 60. So that'd be LOG of 60, and then you take it in your calculator. This would be log of 4, because 20 minus 5, log of 20 minus log of 5 is log of 20 over 5. And this would be using the power rule, 2 log base 3 of x. And that just means if you have a power, you can bring it what? Out front. This is very helpful in solving equations with logarithms. Very helpful to bring that 2 out front. Because anytime you get rid of an exponent, it makes things what? Easier, Hubert. That's right, class. Thank you. 2 log base 3 of x.
What was the
Definition of a logarithm, hold on, is right there. Y is equal to log base b of x yields b to the y is equal to x. In other words, what is a logarithm? A logarithm is a glorified exponent, or an exponent on steroids. That's all it is. It just goes faster, it climbs faster than an exponential graph. That's why you use logarithms in biology a lot, especially with dang old bacteria growth and dang old amoebas and stuff like that, because it grows at such a high rate, even past exponential. So that's why you need logarithms a lot in biology. You also use logarithms with and exponentials, glorified exponentials with chemistry, especially carbon dating, half-lives, things like that, when you're talking about either decaying at a certain rate or growing at a certain rate. You really don't see a lot of logarithmic, and I know in civil engineering you don't see a lot of it unless you have a science approach to something, a scientific approach, which would encase biology or chemistry. Usually you don't see, and now when I was in civil engineering, you had to take 2 electrical courses, and they use logarithms in there a little bit. We call them ECE, I think it was 411, 412 or something. I don't know if you still have to take that or not. But I guess so you wouldn't electrocute yourself while you're in the building that you just designed or whatever. I guess so you could check the wiring, I don't know. But anyway, here's some examples of solving the logarithmic equation. So this is how you use the definition. Now this is a kind of a review PowerPoint, so I don't go over a lot of detail, and that's what this is, review. So take and I don't like to use the z because we're not into 3 dimensions yet, and I don't like to use that. Okay, so use the y is equal to log b, and use that definition of a logarithm to solve these guys right here. If you can't, then what should you do? Throw your pencil down in disgust, quit, and go get a drop sword. That's what you should do. Okay? You know how you throw your pencil down in disgust, make it pop up against the notebook paper? You ain't never done that. You will. Some of you are going, okay, I know how to do this. I remember doing this. And some of you are like, I know, I've been there. Now, let's see if this is going to work. There is a delay with this. I don't know. Oh, y'all saw it the other day. So, what I like to tell students to do is take this over here and rewrite it like this, or rewrite this like this. Here we've got 12 is equal to log of 4t. So that looks like that right there. So y. Y is equal to log base b of x is equal to, or yields, b to the y is equal to x. So now I'm going to put this right up under here. 12 is equal to log. What is it if there's nothing there? 10. It's log base 10. Quit trying to confuse the rest of the class, okay? You're a failure. All right, so what's b? 10. So 10 to the what? To the 12 is equal to 4t. Oh my gosh! We got a simple pre-algebra problem. It didn't write my final part. There. Divide by 4. And t is equal to 10 to the 12th, some BA number. Y'all figure that out on the calculator. Okay? So that's how you use the definition of logarithm. So now that you know how to use it, go ahead and do 2 and 3. Go ahead and do 10 to the, I'd go ahead and do 10 to the 12th over 4 on the calculator as well. You don't want to start messing with something. Don't change horses in midstream. You could change it to 5 over 2, 5 to 12 over 2. You wouldn't need it. I wouldn't mess with it. Now take your handy dandy definition and do the second. So 1/2 is equal to log base 10 of x plus 3. So what is b? To the, oh my gosh, that's number 6. Exponential rule number 6. The square root of 10, which is 3.1, right? How did I know 3.1? Because square root of 9 is 3. So what's square root of 10? No, let me use my calculator. 3.1 is equal to x plus 3. And then 3.1 is equal to x plus 3. And x is equal to, what's 3.1 minus 3? 0.1. What's negative 3.1 minus 3? Negative 6.1. You heard that, class? Now you do the third one. Is that coming back now?
Yeah.
Yes, Hubert. Thank you, whole class, for interacting. One person out of 19 interacted. The rest of y'all suck. You got a TV in the back of the room. Wow. It's got a VCR. Who uses VCRs? Only at Tracking Tech. Yeah, we don't have pencil sharpeners, but we got dinosaur equipment. Okay, this one's turned the other way, so what do? Quit, right? Throw your pencil down. That is so annoying. So, you don't have a logarithm, so what do? You put it on the other side. 20. What?
They don't love me this.
I have been calling them without recording. See, I'm the only one that records the classes. I think there's somebody in the science department that does. It's a woman, I think. But this is the first time we've actually recorded with this Epson and the whiteboard and using this technology with this thing. Okay. Huh? Well, I've already called them the week before classes. I asked them to come figure out. It's a configuration problem, I think. I think the software on here, or the software with this thing, needs to be configured a little bit better with the software on this thing. That's what I think. But then I called them, sent another email on Monday saying, okay, I need this fixed. This is annoying. So I haven't heard anything. So 5 to 2x. So what do? Well, what's B?
2x.
B is what? 5. 20 seconds later. Log base 5 of what? Well, y is what? 2x. That comes over here. And then, so now, what do? Quit. Change base formula. What's the change base formula say? If I've got a different base, I take log of 20 over the log of 5, right? So 2x is equal to log of 20 over the log of 5. And that's the calculator thing. And that's 2x. It don't look like 2x. Let me change it. Have y'all noticed that this circle stays right here and it's supposed to be with this? Have you noticed that? So somebody give me to 2 decimal places. What is this? Please? Oh, I thought you were doing it. Somebody did this on the calculator. Where you at? 1.86. And then divide that. You know, I do this for y'all. Y'all know I do all of this. I do it for y'all. Y'all know that. .86. There. And what is that? 0.9293 or something? What? 0.93. So x is equal to 0.9. Manipulation of an equation, that's what you're doing. Manipulation. If the equation looks like this, you can make it look like this and give you the same answer. Okay? That's all calculus is. Manipulation of a problem. Hopefully that'll knock some cobwebs loose. But what if you don't have a situation you can't use this? What do? Quit. I'm trying to. Okay, why can't I? There. That's the page I wanted. All right, solve those. Well, where did my definition of logarithm go, Hubert? You don't use the definition of logarithm. You might, but what do you do first? What does the top say, Hubert? Take the what? Now, why? How do you know to do that? Because you've got a lot of what in the exponents. And whenever you have a lot of unknowns, variables in the exponents, chances are you might have to take the log of both sides so you can bring them down using the power rule. See how this plays into manipulation of problems. Huh? You don't use the formula, you take the log of both sides. And then use the power rule. I thought I said that. I don't know if you want to do it exactly right. I'm sorry, medication. I'm sorry. First person, you don't. Now you can manipulate the first one a little bit before you take the log of both sides. What can you do? Move the what? 9. Move the 9. And that way you have a nice little problem. I tried to start you off with an easy problem first. Now somebody tell me what you can do. I'm sorry. Move the x to the front using the power rule of logarithm. And what does that do? It makes the problem to where you can what? Solve it. Because it brings the x down to the same level, and all you do now is divide by what? Log of 3, which is a number. And you need to get used to that. This is not log of 3. This is a number. So when you've got a complex rational expression or a complex logarithmic expression, you need to treat this just like a number. So just divide by that number. And x is equal to whatever that comes out to be. Okay, it's not right anymore. It's amazing how it just stops. There it is, x. All right, do this one. log of 16 to the 2x is equal to log of 2 to the 4x. Use your power rule. Bring it out. So 2x, this whole thing comes out, it's 2x log of 16 equals 4x minus 1 log of 2. Now remember, what did I tell you this was? It's a number. So what else do you do with a number when you're in front of parentheses? Distribute. Okay, you got to bust up that block because there's an X in that block. So if it makes you feel better, somebody change that into, what is log of 2? What is it? I'm sorry, what? Okay, change it to 0.30 if you have to. Okay, change that to 0.30 or whatever. And now you've got written 0.30. There. So distribute that 0.30. If you don't like distributing the log, distribute the 0.30. Because that's the same thing. 2x times the log of 16 is equal to log of 2 log of 2 times 4x minus log of 2. And you can change this to 0.3 and change this to 0.3. Go ahead and change this. So let's go ahead and do all that. 2x times, somebody take the log of 16, what is it? Just give me a 100 to the 100. Point what? 2 places. 1.20 is equal to 0.3 times 4x minus 0.3. And now you're back to pre-algebra. I'm sorry, algebra 1. So finish it out. So 2 times 1.2 is what? 2.4? .3 times 4 is 1.2. Okay, there's a voided area down here that, yeah. So bring the 1.2 over, right? That'd be minus 1.2. So that'd be 1.2x is equal to negative 0.3. Y'all check me on that. Divide by 1.2. Divide by 1.2. Okay, well, you get the point. Now, the problem with this is there's no solution. Why? Because you can't take the log of what? Well, you can put it back in here. I'm sorry, it's not a log. You can put it back in here. So what do you come out with? What's 0.3 divided by 1.2? 0.04, what? Negative 0.25. So that's your answer. X is equal to negative 0.25. Again, you're manipulating the problem. You don't know how to get the answer, so there's 2 options. 1, you quit. 2, you figure out a way to get it in a way that you can solve it. And people say, well, why do we need calculus? Why do we need algebra? Well, I want somebody that's building a bridge that I've got to go across. I want them, when they get to a problem, I want them to figure out a way around that problem, not quit. Because the bridge fall down if you don't find a way around these problems. Okay? All right, do that one. And then that'll be our review on logarithms. While y'all are doing this, I'm going to do something right quick if I can. So this is going to be log 3 to the 2x plus 1 equals log 12. 2x plus 1 log of 3 is equal to log 12. Now, you can distribute to get rid of the parentheses, or you can divide. In this case, I would divide because, you could still distribute that through here, or you could divide. And the last problem, I don't think it would have helped us. It could have. I don't know how to have to go back and look. But I'm going to divide by what? Log of 3. And then it's going to give us 2x plus 1 is equal to, somebody give me log of 12 divided by log of 3. 2.2 what? 2.26. Now, you can finish it.
It would be log, if we divide it, like says log 12 divided by 4 would be log 4.
Does it come out to be the same? And then subtract 1. And that's going to be 1.26, and half of 1.26 is 1.13. Help me out. Or 0.63, I'm sorry. X is equal to 0.63. And for some reason, this board does not like to write x's below this area. X is equal to 0.63. So that's a little bit of review on logarithms. We feel good? Hopefully that knocked some cobwebs loose. Let's go to rationalizing the denominator. I got a couple of emails on that, but y'all suck at it pretty much. And I'm trying to get out of this, so y'all just bear with me. There we go. And I want to get out of that. Alright, y'all gotta look for rationalizing the denominator. It's not in, it's radicals, radicals. This is totally different from my computer at home. Okay, now with all radicals, and I have to go through this because it's important. I love to do the cube root of something and somebody say, oh, well, that's the cube root of 8 is, or the cube root of 64 is 8. No, the cube root of 64 is 4. When you're doing radicals, you have to think in terms of the index. When you see an index of 2, you automatically go to the square roots. When you see an index of 3, you automatically think cube roots. All right? You have to make that shift. If you don't make that shift, you're going to get the wrong answer. All right? So just a little bit of warning to you. And there's perfect cubes, perfect fourths, perfect fifths, and so on. You have to remember these things. I don't tell you to remember all of these. I usually tell students to go up to 5 on the fourths and go up to 3 or 4 on the fifths, because that's a lot of problems in mathematics books usually go up to 5 here and 6 here unless they want you to use a calculator. But you have to think in terms of these indexes. Okay? And there's some, I'm not going to go over those, but I think y'all know the square root of 100. I'm sorry, square root of 100, depending on where you're from. Cube root of 64 is 4. Square root of x squared is absolute value of x. Remember, when you take the square root of a even exponent, you have to put the absolute values around it, because -4 quantity squared is positive 16. So you have to put the absolute values around it, okay? And what do you do in these cases? What do you do? And I'm just going to go over this for review purposes. When you see something like this, what do? 2 options: quit or manipulate. I'm going to go ahead and tell you this. There's not any quit answers in calculus. So what does that leave? Manipulate. So break this up into the square root of 2 times the square root of 25. And the square root of 25 is 5, square root of 2. And you should be able to do that. But when you get to this one, you got to think in perfect cubes. What perfect cube will go into 48? 16 is not a perfect cube, is it? I thought I was thinking more of 8, because, see, y'all just did what I told you not to do. 16 is a perfect what? Square. You did exactly, you took the bait, hook, line, and sinker. All right? What 8? What's 8 times what will give you 48? I'm sorry, what? Yeah, it's 2 things. Articulate and enunciate. When I ask y'all a question, y'all do, that's what y'all sound like. Enunciate. 8 times 6. So the cube root of 6, or cube root of 8, times cube root of 6. Now what's cube root of 8? 2. 2 times cube root of 6. Okay? What's the square root of x to the 5th? We can't take the square root of x to the 5th. You have to think in terms of 2, because that's a 2. There's nothing there. It's a square root. So I've got to take the square root of what? X to the 4th. So I'll break this up into the square root of x to the 4th times the square root of x to the 1st. And what's the square root of x to the 4th? X squared, Hubert. That's right, class. Times square root of x. I'm sorry, what? Okay? This, I cannot take the square root of it. So I have to change it into something I can. Why can I take the square root of x to the 4th? Because 4 is divisible by 2. So I change it to x to the 4th times x to the 1st. Because 4 plus 1 is 5. Does that help? If I gave you the square root of x to the 7th, what would you change x to the 7th to? X to the 6th times x to the 1st. Because 6 is divisible by 2. You got it? Same thing here. What would I change x plus 1 to the 3rd power to? X plus 1 to the 3rd power, x plus 1 to the what? 2nd power times x plus 1 to the 1st power, and take the square root of x plus 1 to the 1st, put it in absolute values. Square root of 8 break it up into, and y'all can work on those. I mean, write them down if you want to, take a picture, whatever.
The fifth root of 64, that would be 64. One would be 67.
Well, you have to think of the perfect fifth roots. The first one that I think of is 32, which is 2. 2 to the fifth power is 32. So you break it up into the fifth root of 2 times the fifth root of 32, and the fifth root of 32 is 2. These things that I showed y'all back here, well, I'm trying to get there. Where is my... Okay, I'm going backwards and I don't have the... Maybe a backspace. There. These are very important. When you're dealing with radicals, the first thing you should do is get 4 or 5 index cards and put these on. Because you've got to think, it's like this. Let me ask you a question. Some hotels, I've spent the week with my son in New York, and even today, there's still hotels that have what on each floor besides rooms? Coke machines, right? I'm sorry, soda pop machines. Down here we call them Coke machines. All right? What do you have to think in terms of, with the old, before we had the swipes and before we had the dollar things, what did we have to put in the Coke machines? Change. All right? Now, did you go up to the Coke machine and have 100 quarters? I mean, 100 pennies? No. Why? Because you have to look at the little sign on the Coke machine back then and see what it took. All right? Did it take 50-cent pieces? Did it take Susan B. Anthony dollars? Did it take quarters or what? Back then they took quarters. All right? And you put 2 quarters in it, 3 quarters in it, dollar, whatever, and it gave you. So you have to think in terms of quarters with a Coke machine. You didn't think in terms of pennies. See what I'm saying? So if you wanted Cokes for the whole night, you had to go down to the front desk and get $5 worth of quarters. You didn't get $5 worth of dimes. Why? Because the Coke machine takes what? Quarters. See what I'm saying? When you deal with radicals, you've got to be in terms of the index. If you don't think in terms of the index, you're going to get them wrong all day long. Dang old Coke machine. All right. Operations. I'm not going to... The square root of x, if they're alike, you treat it just like a variable. It's a label. 2 boxes of cereal plus 3 boxes of cereal equals 5 boxes of cereal. The boxes of cereal don't change. This don't change. When you multiply, it does. When you multiply, you just do it. Square root of 5 times square root of 6, square root of 30. So that's a little review over that. But division is where you get into the rationalization. And you're using the conjugate. No coughing or sneezing in class. Okay? So look at that one. I've got x plus 2 over the square root of 2. The first thing that comes to my mind is there is a radical in the denominator. That sucks. I got to get rid of it. So I got to multiply by a factor of 1. So whatever that radical is, I've got to multiply by itself over itself. Now what if that was a cube? Well, the cube, totally different story. If I have the cube root of 2 right there, then I've got to multiply by the cube root of 4 over the cube root of 4. Why? That's not rhetorical. I mean for y'all to answer it. If I had four over the cube root of 2, I would have to multiply by the cube root of 4 over the cube root of 4. Why? I'll tell you why. Because Okay, hold on. I do this for y'all. Y'all know that, don't you? I go through all this hassle for y'all. Because I remember my perfect what? My perfect cubes. Some of y'all are thinking perfect squares. You've got to switch gears. That Coke machine don't take quarters. It takes what? Dimes. So you've got to go down to the front desk and get your $5 worth of quarters turned into what? Dimes. Because you can put quarters in that machine all day and it's not going to what? It's not going to give you anything. You can think in terms of these all day long, but if you've got a cube in front of that radical, it's not going to help you at all. So, what's the first perfect cube? 8. So I'm going to multiply my cube root of 2 times what? So I can get the cube root of what? Yep. I heard a light go on. Somebody said, oh, that's good. So, that's 4 times the cube root of 4 over 2. And I got rid of the radical. That's called rationalizing the denominator. Now, I didn't use conjugate because you don't have 2 terms. This is just multiplying by itself over 1. That's what I used to do. I didn't know that was there until just now. Sorry. But see, that cube root, that changes everything. I got $5 worth of quarters. Ain't worth crap. You gotta go downstairs and change it. Yeah, you can do that. I'm not worried about that. I'm just worried about you being able to rationalize the denominator. Okay, yeah, that would come out to be 2 times the cube root of 4. You reduce this. Thank you, Miss Anderson and Kapler Faith. Whatever. Now, what if you have 2 terms? You either quit or manipulate. Or not know how to work the program. There we go. So, what are you going to use? Well, you're going to use the conjugate. Now, I hate to be graphic, but you see movies all the time, and they have prisoners, and prisoners have conjugal visits, right? What does conjugal visit mean? Well, I'll let you define that, but it means opposite comes in, the opposite sex, okay? That's what conjugal means. I don't know what it means now, but back when I was watching movies, you know, somebody have a conjugal visit, all right? Conjugal, conjugate, conjugate, conjugal, opposite sign, opposite inverse, opposite operation. So the conjugate of x plus 2 is x minus 2. The conjugate of x minus 3 is x plus 3. The conjugate of the square root of 2 plus x is square root of 2 minus x. The conjugate will give you shortcut number 3. You're not going to get away from those shortcuts. Never. The day you get away from those shortcuts is the day you stop using math in your job. You're never going to get rid of those shortcuts. So for that person back in algebra that said, well, I can do the reverse FOIL, that's why you fail math. That's why you can't pass calculus, because you're not using the tools that are available for you. It's like trying to drive a nail in a 2x4 with a screwdriver. You can't do it. So, you have to look at the denominator and decide what the conjugate is and what that does. And we'll do this one right here. Let's do the first one. What does that give you on the bottom? Shortcut number 3. So I'm going to take my handy dandy jigger here, and I'm going to say 2 times the square root of x minus 2, and there's nothing I can do there except distribute. I don't care about the numerator. I want to get the radical out of the denominator. So on the bottom, I'm going to put it in shortcut number 3 format. So square root of x squared minus 2 squared. And what will that do to the radical every single time? No, y'all remember class. Okay? What does that do to the radical? Cancels it out. So now we have 2 times the square root of x minus 2 over x minus what? 4. And that's your answer. Now you do these 2. While y'all doing those 2, I'm going to call the roll. I think everybody's, well, let's see. 1, 2, 3, 4, 5, 6, 7. One person's missing, so I got to go through the whole roll. Y'all suck. I got to learn how to use this. This system is different from mine at home. Oh, I do have something to show you though. I bought another piece of equipment for my little endeavor. Dang old document, dang old cam. So that way if somebody sends me a homework question that they need right away, I can actually do it on the dang old camera. Alright. The thing folds up, you can put it in your pocket. Versus the first ones we have, I got one of the old ones like in my office, and it looks like a dang overhead projector. Now you got them fold up in your pocket. Oh, you didn't see it because the screen's frozen. I'll show it to you in just a minute. Like y'all really care. But if you need a homework problem over the weekend or something, and I'm not passed out on the couch or something then for 2 days, then I can help you out. It's a joke. Ha ha. My teacher's an alcoholic. Let's see. How do you think I deal with students? Set attendance. So everybody's here except for one person. So I have to go through the whole list. All right. Ahmed, Anderson and Anderson are here. Caldwell, Clint Scales is here. Cook,
Here.
Briggs, Grant, Hernandez, Huth, Johnson, Jordan, Marshall, Tail, Fan, Scobie, Selly, sorry. Is it Sealy? Sealy. Shake, Silver, and Tucker. There's the one that's not here. And of course, which one is it? The last one. Murphy's Law. All right, let's go back to our radicals and slideshow. And I hit the wrong button. Great. I ain't doing that. That takes too long. There we go. So, in this case, we multiply by this is going to be 4 times the square root of x plus 3 over the square root of x squared minus 3 squared. And that cancels that out. And that's going to be 4 square root of x plus 3 over x minus 9. And this one's going to be 4 square root of x plus the square root of 2 over x minus 4. Yeah. Yeah, I mean, you could put 4 square root of x plus 4 square root of 2 over x minus 4. But these are just some problems I thought up in my head just to show you the conjugate. You got to know what the conjugate is, and you got to know how to use the conjugate, and you got to use shortcut number 3. Does that help? Hopefully it knocks some cobwebs loose. Just a little review, don't forget the i's, the square root of a negative number. In other words, if I give you the square root of negative 25, let's say you're doing the complete the square. I can't write with a mouse, so don't make fun of my mouse writing. The square root of 25, negative 25, you get that with complete the square. What does that tell you about the x-intercepts? Well, if you get the square root of a positive number, that means there's how many x-intercepts? 2. If you get the square root of 0, what does that mean? There's 1. What if you get the square root of negative? There's none. So you need to write that down. That's called the discriminant. Okay? I don't know how to spell it. Spell it however you want to. I'm not going to spell it and then you make fun of me saying I can't spell. So I'm just going to tell you I don't know how to spell it. I think it's like it sounds with I's and then A and T. Okay?
So you're saying the discriminant is that the negative number can't be on x?
That's what it means. In other words, square root of a positive number is equal to 2 x-intercepts. The square root of a 0 is equal to 1 x-intercept. And the square root of a negative number is equal to no x-intercepts. 0 x-intercepts. Okay? So what do? Well, you go out to the side, you write your y-intercept, you write your vertex, but where it intercepts, you say no x-intercepts. So you know you've got a floater. I saw that. That was a yawn. All right? A floater, meaning that your parabola is out in one of the quadrants doing what? It's floating. It's not crossing the x-axis. I call them floaters. All right? So you just got to write your term. So you get to the point where you get the negative square root of 25 and then you just quit. No, because some teachers want you to write it in terms of I. So you're doing this and you get this and you go, okay, well that's equal to the square root of 25 times the square root of negative 1. And what's the square root of 25? And then what's the square root of negative 1? I. And the reason, you know what the reason for I is? To give you something that you can logistically add and subtract, multiply, and divide. That's why. You can leave it as a square root of negative 1 if you want to. There's nothing wrong with that. But let's see. Square root negative 1. I. Which one's easier to write? I. So that's why people use it. Okay? Is it 10 o'clock yet? Well, why are they coming in? Right there and somebody hit him. I'm kidding. Alright? So, remember this, because if I give you something like, what's I plus 2 times I minus 2? Well, Hubert, that's shortcut number 3. Yes, that's right, class. Which is I squared minus 4. But I squared is what? And then 1 minus 4 is, and your answer is negative 5. And you go, oh, that's why. I don't know what this is. What does this say? You can take the odd index of a negative number. So that's why you don't have I with cubic functions. Question. Right, complaint. We're just hit and miss. I understand that some of y'all are taking some of this in. Some of y'all hadn't done it in years, and I understand. Here's operations with I. You get rusty. I plus I is 2I. 3I plus 2I is 5I. 10I minus 3I is 7I. Same thing as your x. That's why they developed. That's why they created I. They didn't create I and say, well, let's find a way to confuse students even more. No, it's the alternative. In other words, they want you to get rid of the square root of -1 as fast as you can so you can apply algebraic properties to I. And that's why. This thing is starting to bother me. Why does it keep coming up? All right, multiplying I is just like multiplying x. But you have to remember that I squared is -1. So use your FOIL method. You get the same thing as you would with x, but this guy right here is what? -1. And you've got to remember that. Division with I, same thing. But what about I to the exponent? Remember I to the exponent? This is just a little refresher. Use Hubert's rule. I is a fraction of the class, 1 is a whole. If it's even, it's positive. If it's negative, it's odd, it's negative. Write that down right quick because that'll help you out. Will you ever see this in my class? Probably not. Will you see it on a standardized test? Yes. So what do? You take the exponent and you divide it by 2. Why? Well, that tells you what you get. If you get a whole number, then it's I. The whole number, 1 is a whole, it's 1. If you get a fraction, that means it's I. So let's look at 26. 26 divided by 2 is what? Is 13 a whole number? Yes, so your answer is going to be 1. Now, what is 13? Odd or even? Odd, so it's -1. Here's the alternative for that. 44 divided by 2 is 22. Whole number, your answer is going to be 1. Even, it's going to be +1. So if you multiply these I to the 44, I times I, I times I, I times I, 22 times, if you do all the math, you're going to get a +1. So what about 25 times 2? Well, 25 times 2 is 12 and a half. Well, what is 12 and a half? Is that a fraction or a whole number? It's a fraction, so your answer is going to be I. Is 12 odd or even? So it's positive I. And then 27 divided by 2 is 13 and a half. That's a fraction. Your answer is going to be I. Is it odd or even? So it's -I. So that's kind of a little refresher on radicals. Does that help? Everybody's supposed to say yeah, but I'll take one yes. That's fine. All right. Oh, I was showing y'all there's my document camera. You fold that little thing up, and that thing right there is about 5 inches by 2.5 inches. Can you believe that? And like I say, the one in my office that I got like 2 years ago, or 2 years ago, it's like an overhead projector type thing. I just think that's neat. Technology. But we don't use math in real life.
Let me get a selfie stick and fix it and put your phone in it.
That won't work, no. Video, that won't work. All right. Now, let's look at identities. Now, what I'm going to do is pull up the trig identity sheet. And it's real nice. You get to pull it up and you can print it out all day long for the 2 or 3 people in here that's going to actually do that. All right? Dang old hit images, and there you go. All the sheets you want. Now, the one I usually pick is this one. Okay? There it is. And you can hit view image, and you can pull them up like that. All right? The first ones you need to know are these up here. These first 3 boxes. So what I would probably suggest to you is go home and print this thing out and laminate it, and I'll let you use it. You can use it on your test or whatever. I don't care. But you need to print it out and use it. You need to print out and use your unit circle, and we will talk about that also. It's very easy to do the unit circle. You don't have to memorize it. All you got to do is just know your 30, 60, and 45 degree angles, which, we're going to talk about that a little bit here in just a few minutes. I'm going over a little bit of trig. And really, you need to go over a little bit of trig before you go over the trig identities. But we'll go ahead and hit the trig identities. These are called your reciprocal identities. That's the cosecant is equal to 1 over the sine, is which if you take your Oscar had a hunk of apple, you can pretty much come up with that. You don't have to think about it too much. This is not the color I want. Hold on just a second. There it is. I'm going to go to this right quick. And for those of you that remember your trig, sine is equal to Oscar had. Cosine is equal to a hump. And tangent is equal to of apple. Okay? Don't be one of those people. I did that one time. Oscar had a hunk of apple, and some clown was in the back of the room. I don't understand what you're talking about, Mr. McClure. And I'm like, Oscar had a hunk of apple. Oh, well, I learned Sakatoa. Shut up. People like that just irritate the hell out of me. I mean, it's the same what? It's the same thing, but that person had to go, oh, I didn't learn it that way. I learned Sakatoa. Anyway, I just went ahead and kept on adding more. Anyway, the reciprocal of the tangent is the what? Cotangent. So that's A over O. And you need to take that same reasoning and apply it to the reciprocal identities. Because if you go to the reciprocal identities, hold on, that's not supposed to be there. That thing right there is not supposed to be there. I hope it don't mess up y'all's recording. If you go to the reciprocal identities, what is the tangent? 1 over the cotangent. So if you remember your basic Sakatoa, if you remember that, then you can remember the reciprocal identities and not have to memorize them. These two are very important. These two right here help you with conversions. All right? Sometimes you're asked to change identities or verify identities. The first rule of identities is to put everything in terms of what? Sine and what? Sine and cosine. And that's what helps you there. These are also important. Now, why ain't I showing you any of these? Because you ain't going to be able to do squat with these unless you what? Know how to use these and learn those. So that'll be your homework tonight, is learning those. And then what we'll do when y'all come back, whatever day y'all come back, that we'll move into some of your homework into verifying and proving some of your other ones. But you got to learn these first. Okay? I'm not going to go into that yet. Now, just to go over a little bit of review, and I've got 9:35. I got a few more minutes. I want to pull up one of my reviews on trig, and this is just a. Okay, where is it? Where? Thank you. I hope that's the one that I just did. I think it is. Yeah. All right. And this is just a little review of trig, and then of course we'll get into the identities. Of course, trigonometric functions and trigonometry come from trigonometry, which means basically measure of a triangle. Okay? Dang old history, dang old Greek trigonon or whatever, trigonon, which means measure of a triangle. And you can get into all kind of little things with the radius and how the radius is the hypotenuse and all that good stuff. I'm not going to go into that, but we know that there's acute angles which are less than 90 degrees. We know that there's right angles, obtuse angles, and straight angles. A radian is an angle with a vertex at the center so that you got a 1-to-1 ratio. Dang old radius is 1-to-1. So that's what that is, 1 radian. Put that in terms of theta, and we'll get to radians in just a minute. There's the unit circle. There's the guy that you need to memorize. And it's not that hard to memorize if you know your, I'm skipping ahead a little bit. If you know your, well, I don't have them up here, but the special angles. And the special angles are the 30, 45, and 60 degree triangles. And if you know those, you can pretty much do the whole thing without even memorizing it. Does it take you longer? Yeah, it takes you a few minutes longer to do the unit circle, but you can do the unit circle at any time. You don't have to memorize it and worry about forgetting something. You can just write it out. Anytime you need it, you can just write it out. And I'll show you how to do that next week. The quadrants shows you acute and obtuse, but it also shows you the readings. Don't forget the readings that you need to tell what quadrant you're in as far as a trig identity. And a little bit of the SOHCAHTOA is here. And there's your triangle, right triangle, and theta, opposite, adjacent, hypotenuse. And there's your Oscar hat, a hunk of apple. And there's your little man. A lot of people have no idea what the little man is. Probably don't. The little man is always on the angle, and his feet are always on the adjacent and the hypotenuse. And he's always staring at what? He's always staring at the opposite. And if you will always remember that, then you won't get confused with your angles. I'm not talking about now. Now I know you know what theta is. But if they ask you to move theta and put it somewhere else, then you remember the little man has his foot always on the hypotenuse and the adjacent. Therefore, you always know where the opposite is. And that's very important, especially when they change theta on you. Okay, because theta is not always going to be the same. You'll see others like this, and that's, normal. I do that. And you also need to know the Pythagorean theorem. Of course, y'all probably already know that. And the terminal side, got to that, I was getting to that. That's a little problem there. So if you can find the 6 trigonometric functions of that triangle right there, then you're good to go as far as an introduction to trig. So, what are we going to do next week? We're going to spend probably, what's today, Thursday? We're going to spend Tuesday on trig identities and finishing up the review. All right? That's what we're going to do. I need you to make sure you know how to factor, how to use the shortcuts, how to rationalize the numerator and denominator. What I mean rationalize the numerator and denominator? Well, make up a problem. You don't have to need me to make up a problem. Just take and turn your rationalizing the denominator problem right down. Square root of x plus 2 over 6. Now, why would you have to do this? Well, because sometimes they give you problems with limits to where you've got to get rid of the radical. And sometimes they give you the radical in the denominator, and sometimes they give you the radical in the numerator. And if you need to get rid of the radical in the numerator, you multiply by the conjugate. Square root of x minus 2. Square root of x minus 2. And that'll give you what on top? X minus 4 over 6 square root of x minus 2. Now, why? Because limits are different. And limits you're trying to get to, limit as x approaches 0. And you're trying to find the limit of, I don't know, blah, blah, blah over x. Well, what's wrong with this problem? You can't have what in the denominator? So it can't be done. There is no can't be done's in calculus. All right? In limits, if you get something that you think can't be done, that's a good sign that you're wrong. Because I'm not going to give you one that can't be done. Something has to be manipulated. The whole purpose for calculus, 3 semesters of calculus, is for you to manipulate any problem into something that you can get the answer. That's the whole purpose for calculus. That way, when you get to the civil engineering, you get to the transportation engineering, you get to the fluid dynamics, you get to all those courses, when you're given a problem, you don't just say, well, it can't be done, I quit. You can't do that. You've got to manipulate. And that's what this is. And the limit, I've got to plug in 0 for x. Well, that's not going to work. So I've got to manipulate this problem, and that's what we're going to be doing probably Thursday of next week, is going into limits and explaining what limits are. Then by the next week, you're going to put the two together. You're going to put the algebra and the limits together, and we're going to be doing what's called the difference quotient. And the difference quotient leads into the derivative. Okay? And Faith has had me, Mr. Clintskills has had me. Who else has had me? Anybody else? Those are the only two. Well, they can attest that I may take a little bit longer doing something, but when I get to the point that where it counts, you're going to thank me for taking the time to get to. Some of y'all that's had calculus before is going to say, "Oh my God, that's so easy." And when you get to that point, you're going to say, "Thank you," because it is. It's real easy. In fact, 90% of calculus is what? Algebra. He's had a good teacher. Who's your teacher? 90% of your calculus problems that you do is algebra. So if you suck at algebra, you're going to suck at what? Calculus. All right? So you need to study the algebra and do as many algebra problems as you can. If you want me to get you some algebra problems, although all you got to do is go on Google and say intermediate algebra worksheets or review for calculus algebra worksheets, that's all you got to do. It's very hard. Do them because it'll help you out tremendously. And you need to focus around exponents, logarithms, rationalizing the denominator, and completing the square and factoring. Those 5 things. Okay? All right, who's got questions for me?
How much time do you have until you're going to come?
I think somebody tell me what time's the next class start? 10? Hell, I don't know. Let me look. Huh? Is it 10:10? 10:10. So if you got any questions, I'm up here. Other than that, I want you to continue to work on the intermediate review or the trig review or whatever's in there. And then come Tuesday, we'll start working on the identities and probably start in the limits. Y'all have a good weekend.
I have a simple question for you.
Yeah.
Okay, so my boss did this one in his head at work, and I was kind of stunned. We had a building that was 109 feet by 75 feet. He was asking how much square footage is that.
Multiply them together.
Well, I'm saying, how well do you do that in your head? He did it in like 10 seconds.
Well, doing it. Well, hold on a second. I got to stop the recording.